So in this video we're going to look at the reactions of alkenes. There's quite a bit in this topic. You've got 4 different reactions that you need to learn, and you've also got a couple of reaction mechanisms. Firstly, what I've drawn is I've drawn an alkane, butane, and I've drawn the alkene, butene. When we looked at alkanes, we saw that they were unreactive. You could combust them and you could react them with radicals, but other than that, they didn't react. And the reason alkanes are so unreactive is because the only bonds you've got present are these really strong carbon-carbon bonds and carbon-hydrogen bonds. For my alkane to react, it needs to form new bonds. And to form new bonds, one of the old bonds would first have to break. Again, because those carbon-carbon and carbon-hydrogen bonds are so strong, you would need a lot of energy to get one of those bonds to break and to enable it to react with something new. So if I just had an alkane, it's not going to react with hydrogen. Underneath, I've drawn out the alkene, and the only difference is that instead of having all single bonds, I've now got one double bond in there. That carbon-carbon double bond consists of a sigma bond and a pi bond. And that pi bond is relatively weak. So it is weaker than a carbon-carbon single bond. And because it's relatively weak, it is willing to break. And when that double bond breaks, when that pi bond breaks, then you are going to have room to form new bonds with other reactants. So in this case, I'm reacting an alkene with hydrogen. When I do that, the pi bond is going to break, not the full double bond, just the pi bond. So I'm just going to draw a single bond between those two carbons. I'm going to fill in all of the old hydrogen atoms that I had before. But what you'll be able to see is because I've lost that pi bond, that I've got 2 carbon atoms here that now only have 3 bonds when they need to have 4. Because I've only got 3 bonds instead of 4, there is room to form a new bond. And I'm reacting them here with hydrogen, which contains 2 hydrogen atoms. So I'm going to be adding 2 new hydrogen atoms, 1 to each carbon. This is called an addition reaction. I am taking 2 reactants and I'm adding together to form one product. In order to be able to do this, that pi bond must break. The pi bond is weaker than the sigma bond, so it is willing to break. The pi bond breaks. That leaves you with 2 carbon atoms that are short 1 bond, and then they can form a new bond. So I'm splitting up my reactant, my hydrogen, into 2 separate hydrogen atoms and adding those hydrogen atoms to each carbon of the double bond, and it's called addition. Okay, all alkenes are going to undergo addition reactions. Actually, sorry, in this case, there is actually a catalyst needed, which is nickel. Okay, but all of your alkenes are going to undergo addition reactions. So I'm going to draw out a few more down here. I'm just going to use skeletal formula though for ease. So I'm going to draw butene again. This time I'm going to put the double bond there at the end of the chain, and this time I'm going to react it with chlorine, Cl2. When I react it with chlorine, I'm going to lose my double bonds. I'm going to draw my 4 carbon atoms again, but I'm going to lose my double bond. Each carbon that was part of that double bond is now short a bond and can form a new one. Chlorine consists of 2 chlorine atoms. 1 chlorine atom goes on to 1 carbon, the other chlorine atom goes on to another. If I used propene this time and reacted it with bromine, again, when they react, I lose the pi bond. I have then 2 carbon atoms that are missing 1 bond. Bromine is made of 2 bromine atoms. 1 bromine goes on 1 carbon, the other bromine goes on the other carbon. Again, it's addition. If I put this in a ring, it wouldn't make any difference, so I can draw a cyclohexene ring. I'm going to go back to hydrogen, H2. As I said, you do need a catalyst for hydrogen. And again, I'm going to draw out, and I'm going to leave out the pi bond because that breaks. That leaves me with 2 hydrogen atoms that are both short a bond, and I end up adding hydrogen to each of them. Now, because it's skeletal, I'm not going to draw in the hydrogens. You can if you want to, but you're going to get a hydrogen adding to each of those carbon atoms. And these are called addition reactions. Another possibility is that you react your alkene with a hydrogen halide. So we had chlorine, bromine and hydrogen. Now I've got a hydrogen halide. So I've still got two atoms, but unlike in the examples above, these two atoms are different. Again, when I'm drawing my product, I'm going to draw it without the double bond. The two atoms, hydrogen and chlorine, I'm going to add one to one carbon. So let's just say I add the hydrogen here, and I'm going to add the chlorine here. If I did that the other way around, so I draw out my molecule, I leave out the double bond. If I put the hydrogen here and the chlorine here, does that make a difference? Well, the answer would be no. If I name these products, I have 1, 2, 3, 4 carbons. The one on the left I would call 2-chlorobutane. And the one on the right I would also call 2-chlorobutane. Remember, you're always going to number to give the lowest number to the substituent. So it doesn't matter which way around I do it, I'm going to get 2-chlorobutane. So they're exactly the same products and I only need to draw one of them. However, if I change this and I just moved the double bond and I reacted it again with HCl, same thing's going to happen as before. I'm going to draw out my alkene, but without the double bond this time. The first time around, I'm going to add the chlorine to the carbon at the end and the hydrogen to that second carbon there. And then I'm going to try it again, draw my 4 carbons. But this time I'm going to put the chlorine on this carbon and the hydrogen on this one. So if I look, it's when I name it that I can see if I've got the same product or not. So here I've got 1, 2, 3, 4. I've got 1-chlorobutane. And then over here, I've got 1, 2, 3, 4. I've got 2-chlorobutane. So in this case, it does matter. I am getting different products depending on which way around I add my chlorine and add my hydrogen. And in general, this is always going to be the case if you've got an unsymmetrical alkene. So if I look at my alkene here, there's no difference between the two carbon atoms of the double bond. They're both bonded to a CH3 and they're both bonded to one hydrogen. The two carbons are identical, so it doesn't matter which way around you add the atoms. In this example, the two carbon atoms of the double bond are not identical. The carbon at the end is bonded to 2 hydrogens, the second carbon is bonded to 1 hydrogen, and then this C2H5 group. So when the two carbons of the double bond are not identical and you are adding 2 different atoms, you're going to get 2 different products. If we look at the examples above here, these 2 carbon atoms are identical and I'm adding 2 of the same atoms anyway, so it doesn't make a difference. Up here, these 2 carbon atoms are not identical, but they're each getting a bromine, so it doesn't matter which way around I do it. And same here, these 2 carbon atoms are not identical, but they're each getting a chlorine, so it doesn't matter which way around I do it. So you're going to get 2 products if you've got unidentical carbons or an unsymmetrical alkene, and you're adding 2 different atoms. We've got a few more examples to look at. And then I'm going to get you to do some for yourself, and then we'll have a look at mechanisms in a moment. So if I drew something like this, I'm going to draw a ring. When I draw my alkene like this, both of those carbons are identical, but if I add another substituent, now they're not. This carbon is closer to the methyl group than this carbon is, so they're no longer identical. So if I react it with hydrogen bromide this time, there are 2 different products I can get. So if I draw them out, I'm going to draw the molecule each time, but without the double bond. In the first instance, I'm going to put the hydrogen on the first carbon and the bromine on the second. And then the next time I do it, I'm going to draw, again, I'm drawing it all out, but this time I'm going to put the bromine up here and put the hydrogen down here. So if I were to name this, I would get 1-methyl, 3-bromo, sorry, I'll actually write it as 3-bromo, 1-methyl cyclohexane. Here it would be 2-bromo, 1-methyl. So again, I've got a 1-3 relationship and a 1-2 relationship. They're not the same thing. There's one other reaction you need to know. It's when you react an alkene with water. So all of the reactions that we've looked at so far, you've only had 2 atoms. You add 1 atom to one carbon, the other atom to the other. Now you've got H2O, so you've actually got 3 atoms in there. You need to know that water splits up to give you a H and an OH. So hydrogen will add to one carbon, OH will add to the other. So in this case, I can put hydrogen there and OH there. If I did it the other way around, because my alkene is symmetrical, I do end up getting the exact same. I'm getting the alcohol group on carbon 2, whichever way around I do it. If we look at a different example, reacting it with H2O, I draw my, again, without the double bond, put an OH on one and a hydrogen on the other. Or I can put the OH on the end and the hydrogen there in the second one. In this case, it is different. You've got OH on carbon 2 or OH on carbon 1. In terms of conditions, just so we are aware of the conditions, when you're reacting an alkene, so I'm just going to draw one alkene here in the center. I'm going to stick with but2ene. When I am reacting an alkene with hydrogen, I need a catalyst, and I need nickel as my catalyst. When I'm reacting my alkene with a halogen, whether it's Cl2 or Br2 or even I2, I don't need a catalyst. And I just get that addition reaction. Sorry, I should do this one out as well. When I'm reacting my alkene with a hydrogen halide, so hydrogen bromide or hydrogen chloride or hydrogen iodide, any of those, again, I don't need a catalyst. And the last reaction, when I react my my alkene with water, these conditions are, it's H2O as a gas, so you're reacting it with steam, not with water, and you do need a catalyst, H3OPO4, you use an acid catalyst. So the two reactions involving halogens, whether it's a hydrogen halide or just a plain halogen, you don't need a catalyst. But with hydrogen, you need a nickel catalyst, and when you're reacting with water, it has to be H2O gas, so you can write H2O gas or you can write the word steam, and you're using an acid catalyst, typically phosphoric acid, and you end up with an alcohol. So we're going to look at mechanisms, but I first want you to just do question 1 in section E. So I've just done loads of these reactions. I just want you to go through them all to get familiar with just drawing the products. Then we'll have a look at the reaction mechanisms and how these actually take place. So press pause, do all of question 1, and then press play when you're ready to see the answers. Okay, so I've done out the answers here. I haven't drawn the hydrogens in because it's skeletal formula. You shouldn't really be drawing the hydrogens in. So here I'm just going from an alkene to an alkane, and I'm doing that every time. I'm just losing the double bond. In D, I've got 2 equivalents of H2, so I can get rid of both of those double bonds and just end up with my alkanes. And you'll see that it's always in the presence of a nickel catalyst when you react with hydrogen. The next ones, I'm just reacting them with the halogens. Again, I'm losing my double bond and I'm adding 1 chlorine to each carbon, lose the double bond, 1 chlorine to each carbon, lose the double bond, 1 bromine to each carbon. Okay, make sure you're adding 1 to each carbon. Those halogens should not be on the same carbon, and also make sure that you still have the same number of carbons in your product as you did in your reactants. It's very easy to just draw an extra line that you don't intend to. With H, I, J and K, I'm reacting with hydrogen halides. Because I have 2 different atoms, it may happen that I've got 2 different products. In H, I don't have 2 different products because the 2 carbons of the double bond are identical. So it doesn't matter which one gets a hydrogen and which one gets a chlorine. They're identical. So my product is always going to be 2-chlorobutane. In the second example, my carbons are not identical. The one at the end is bonded to 2 hydrogens. The one in the middle is bonded to 1 hydrogen and 1 CH3. So I've got 2 carbons which are not identical, and I'm adding 2 different atoms. So I am going to end up with 2 products. If I put the bromine on the end, I'm going to have 1 bromopropane. If I put the bromine in the second carbon, I'm going to get 2 bromopropane. So 2 different products because I'm adding 2 different atoms to 2 different carbons. Here I'm adding 2 different atoms, but the carbons are identical, so I'm only going to get 1 product. It doesn't matter which way around you do it. Remember, carbons in the ring are all identical, so this would be bromocyclohexane, If I put the bromine down here, it would still just be bromocyclohexane. It doesn't matter which carbon you put it on. If there's no other substituents, they're all the same. You do have two different products. These two carbons of the double bond are not identical, so I can add the iodine to this carbon here at the end, or I can add the iodine directly onto the ring, so I end up with this. So just, double check that you drew that one correctly. Often with this one, students tend to drop a carbon and they just draw a single line and they put iodine on the end of it. Make sure you have still got your carbon, that you haven't dropped a carbon when you're drawing your product. The next few examples are all to do with adding water. You'll see that I've got H2O gas the whole way down because I'm reacting with steam, and I've got my phosphoric acid catalyst as well. When you're adding water, you add hydrogen to one carbon and OH to the other. Here, because my alkene is symmetrical, I'm only getting one product, but here I'm going to get two, just like I had with HI above. I get the OH adding to this carbon here, or to the same right onto the ring. Make sure again that you're not losing a carbon. There is a carbon there in between. At the end, these two carbons are identical. Okay, there's no other substituents on the ring, which makes all carbons on the ring identical. So it doesn't matter which way around you do it. You're just going to be adding an OH, and you're going to have cyclohexanol. It doesn't matter where you put that OH. And then down here, your two carbons are not the same, so it does matter. You can put the OH there on the second carbon, or you can put it on the first carbon, and you do get two different products. Okay, so really important that you're comfortable with just drawing the products. Once you're comfortable with drawing the products, we can have a look at the mechanisms and how these reactions actually take place. Mechanisms are worth 4 marks, and again they're the same each time, so once you know how to do them, they should be easy marks. Of those 4 reactions, you need to know the mechanisms for 3, but they are all the same. So I'm going to start off with butane, and I'm going to react it with hydrogen. You don't need to show the role of the nickel catalyst, you just need to show the alkene reacting with the hydrogen. The alkene has a carbon-carbon double bond, and it can act as a nucleophile. Nucleophiles are electron pair donors. And the reason they're willing to donate a pair of electrons is because they themselves are electron rich. Okay, they do have electrons to spare. A nucleophile will always attack an electrophile. An electrophile is an electron pair acceptor. And the reason they're willing to accept a pair of electrons is because they are electron poor. Your curly arrow shows the movement of a pair of electrons. So movement of a pair of electrons. And it's always going to move, electrons are always going to move from an area that's electron rich to an area that's electron poor. So you're always going to start your arrow at your nucleophile and end your arrow at your electrophile. That will always, always, always be the case. So when you're doing a reaction mechanism, you need to identify where your nucleophile is. Where is your area that is electron rich? Then you identify where your electrophile is. Where's your area that's electron poor? And you're going to have a curly arrow starting where you've got electrons, ending where you do not, because it shows the movement of a pair of electrons. Alkenes are nucleophiles. The fact that they've got that double bond makes them electron rich. So I am always going to be starting my curly arrow at the alkene double bond. And I'm just going to draw, remember, covalent bonds just represent a pair of electrons. So this time I'm going to actually draw those electrons in there so we remember what those lines represent. They represent a pair of electrons. And these electrons are going to move and they are going to move towards the electrophile. So I need an electrophile. So electrophile is something that's electron poor. Okay, I've got 2 identical hydrogen atoms. And typically, the pair of electrons will be evenly shared between the 2 hydrogen atoms. However, you do have what we call induced dipoles, which means that although on average those electrons are evenly shared, at any one moment in time, the electrons can be closer to one hydrogen atom than the other. When this molecule of H2 approaches the alkene. Because the alkene itself is a nucleophile and is electron rich, the electrons in the alkene will repel the electrons in the hydrogen-hydrogen bond so that the electrons move away from the alkene to the other end of the molecule. So if the electrons were here and this H2 approached the alkene, the electrons would be repelled to the other end of the molecule, and that creates a dipole. So I can say that this hydrogen is delta positive and this hydrogen is delta negative. Now I've got something that's delta positive. I've now got an electrophile. I always had a nucleophile. Now I've got an electrophile. I'm going to start my curly arrow on my nucleophile and end on the electrophile. So I'm going to start here on the double bond. I'm going to end here on the hydrogen with the delta positive charge. Now what this movement of electrons shows us is that I'm going to be forming a new bond now between carbon and this hydrogen atom. Hydrogen is therefore forming a new bond with carbon. Hydrogen can only ever have one bond. So if it's going to form a new bond, its original bond needs to break. So this bond that holds the two hydrogen atoms together is going to break, and the electrons are both going to move onto the delta negative hydrogen atom. So they are my my first two curly arrows, and I get 2 marks for drawing all of that in, for including my delta positive, delta negative, and including my 2 curly arrows. I now need to show what happens next. So I'm drawing out my carbons again. That bond has now broken. Those electrons no longer exist between the 2 carbon atoms. Instead, these electrons exist between one of the carbons and a hydrogen. It doesn't matter which of these carbons I choose. I'm going to choose this first carbon here, and I'm going to draw this hydrogen. So these red electrons that used to exist between the 2 carbon atoms now exist between carbon and this hydrogen. So these 2 electrons have moved. And we need to see what effects that's going to have. All right, if I look at this first carbon here, this carbon on the left-hand side had a share of the red electrons. In my intermediate, carbon still has a share of the red electrons. So it's not losing or gaining electrons. It's just sharing the same electrons, but with a different atom this time. If I look at my other carbon, however, it had a share of the red electrons. Now it doesn't. One of those electrons belonged to this carbon, and now it's lost that electron. Because it's losing an electron, it ends up with a positive charge. So it had contributed one of these electrons to this pair. Now this pair of electrons is all the way over here, so it's lost its electron and has a positive charge. If we look at the 2 hydrogens, these orange electrons, each hydrogen had contributed 1 electron to this bond. Now both of these orange electrons are with one of the hydrogens. It got its own electron back, but it also picked up the electron from this other hydrogen. So it's gaining an electron, and it's going to be negatively charged. So in my intermediate, I end up with something positive and I end up with something negative. Again, I've got something electron rich and I've got something electron poor. So I'm going to draw another curly arrow. And again, it's going to be from the area that's electron rich going to the area that is electron poor. It's always going from negative to positive. And again, this arrow shows that I'm forming a new bond between hydrogen and carbon. And when I do that, I form this. So those red electrons are there. And then I've got the orange electrons are used to form this new bond. And I end up with my alkane. Now you don't need to show the hydrogens because it's skeletal formula, so I could easily not include these hydrogens and just show the positive charge. You also don't need to show the electrons, you just need to show the arrows, but this is the full mechanism. I'm going to do one more to show you. This time I'm going to do it with hydrogen bromide. This time I do have a difference in electronegativity, okay, so up here I didn't, but down here I do have a difference in electronegativity. Bromine is more electronegative, So bromine is going to have a greater share of the electrons. It's going to be delta negative, hydrogen is going to be delta positive. So straight away I've got my electrophile, and as I said, the double bond is always the nucleophile. So you're going to go from the nucleophile to the electrophile. This bond is then going to break, because if you're forming a new bond between carbon and hydrogen, then hydrogen's original bond must break. Doesn't matter which of these carbons picks up the hydrogen first. Both of these carbons are exactly the same. So I'm just going to put the hydrogen this time. I'm going to put it on this carbon. So again, if I show you what's happening with the electrons, there were 2 electrons in this bond. They are now over here between carbon and hydrogen. This carbon had a share of the red electrons on the left. It's still got a share of them on the right. It's just sharing them with a different atom. But the other carbon that was part of the double bond has completely lost its share of those red electrons. It's losing an electron. It's going to end up with a positive charge. The electrons that were in this hydrogen-bromine bond, one belonged to bromine, one belonged to hydrogen, but now both of those electrons are with your bromine. Because both of them are with bromine, bromine ends up with a negative charge. Again, your last step, your nucleophile, which is the bromine, is going to attack your electrophile, which is the carbon. And you're going to end up with this. Okay? When I'm drawing my arrows, it's really important that I'm starting here on the double bond. Here I'm starting on the single bond. And here I'm starting either on that lone pair or on the negative charge. You can start your arrow in either position. You don't need to show the lone pair on the bromine, but you do need to show the negative charge. You absolutely need to show the positive charge here on the carbon. And make sure you're clear on the difference between the delta positives and then the actual positives negatives. At the start, I've got delta positive, delta negative. That bond has not broken. They are not fully positive or negative. But once these bonds start to break, I end up with something fully positive and fully negative. So be very clear on the difference and know when to use delta and when not to use delta. Again, I don't need to show my hydrogen. I'm just going to do one more example to show you kind of an unsymmetrical alkene. So I'm going to do it this time with, and I'm going to do it with HCl. Hydrogen and chlorine, I do have a difference in electronegativity, delta positive, delta negative. This is my nucleophile, this is my electrophile, start my arrow, end at my electrophile. This bond has got to break because hydrogen can't form a new bond without first breaking its old bond. I draw out my carbons. One of these carbons has got a hydrogen. The other carbon will be left with a positive charge. In this case, these 2 carbons are not the same. So I've got 2 different options. I can go hydrogen on the middle carbon, positive charge at the end, or I can put that hydrogen on the end and the positive charge on that middle carbon. In each case, that hydrogen-chlorine bond is going to break, and I am going to end up with a Cl- in each case. Again, I can draw the electrons as a lone pair on the chlorine as well, but you don't have to. And then to finish the mechanism, you're going to have the chlorine attacking that positively charged carbon. So what you're going to end up with is, for this molecule here on the top, you're going to get, and for the molecule on the bottom, I'm going to get 1 chloropropane and I'm going to get 2 chloropropane. So again, I've got an unsymmetrical alkene and I've got 2 different atoms that I'm adding. So I do end up with 2 different products. And you can be asked which one is the major product and which one is the minor product, which one is more likely to form. In order to answer that question, you need to look at the intermediates that you are forming. So specifically, we're looking here at these carbons with positive charges. You're looking at this intermediate and you need to figure out which intermediate is most stable. The intermediate that is most stable is most likely to form. So the most stable intermediate is most likely to form. Therefore, it's going to be your major product. So if this intermediate was the most likely to form, then this would be the major product. If this intermediate was most likely to form, then this would be my major product. You need to figure out which one of these intermediates is most likely to form. And to do that, you need to see which one is most stable. In each intermediate, the reason they're unstable is because it's got a positive charge on the carbon, and that is very, very unstable. Because it's got a positive charge, it means it's lost an electron. So you've got a carbon that has lost an electron, and that is why it's unstable. In order to stabilize this carbon, you want to donate electrons to the positive carbon. Remember, it's positive because it's lost an electron. So it's unstable because it's lost an electron. If you can donate electrons back onto this carbon, you are going to stabilize it. Other carbon atoms will donate electrons to a positive carbon. This positive carbon is bonded to one carbon atom, so it's got one carbon that can push electrons on and help stabilize it. In the example below, my positive carbon is bonded to two carbon atoms. Therefore, it has got two carbon atoms that can push electrons onto it and help stabilize it. Because this has got two carbon atoms pushing electrons onto the positive charge, it is more stable than up here where I've only got one carbon atom pushing electrons onto my positive carbon. I call this a secondary carbocation. In the example above, I've got a primary carbocation. Secondary carbocations are more stable than primary. Because this is my most stable intermediate, this product that forms from it is my major product, and this product is my minor product. So your major and minor products, it's only an issue when you've got an unsymmetrical alkene and you're adding two different atoms across, but you will have a major and minor product depending on which carbocation is more stable. Again, these mechanisms are all exactly the same. So I want you to have a go at question number 2 in your feedback sheet and then do question number 3. So question 2 goes through the mechanisms. So I've got one for hydrogen, bromine, HCl, and then I've got HBr. The one at the end, I'm forming two different products. So because I've got an unsymmetrical alkene. So try and draw me out the two different intermediates and then label one as major and one as minor. Once you finish question 2, question 3, I've just got more reactions. In question 1, I put all of the same reaction types together. In question 3, I've just mixed them up so you can get just a little bit more practice with knowing your reagents, what reagents are required, and what your products are going to be. So complete questions 2 and 3. Press pause, do those questions, and press play when you're ready to see the answers. Okay, so here are our mechanisms. Again, I don't need to show the role of nickel, so I'm just showing my alkene. I've got my hydrogens. I have got to include the delta positive and the delta negative. It attacks, that bond breaks, and then my hydrogen comes back in here. If you showed the hydrogens on your skeletal formula, that's fine. You don't need to show the lone pair, but you can if you want. Your arrow here has to start from either the negative charge or the lone pair. It can't just start on the hydrogen atom. It has to be the negative or the lone pair, and it needs to be a positive charge on that carbon, not a delta positive charge. Underneath, we've got the example with bromine. It's an unsymmetrical alkene, but you are adding the same atom to each carbon, so you only need to do it out once. Oh God, what have I done? Sorry, I've drawn the wrong product there. Apologies, I haven't there, but I have there. So if you look at what I've done, you can see that I drew both of the bromines on the same carbon atom. That is incorrect. I should have one bromine on each of the carbon atoms. So apologies for that. So this is what you should be forming. So again, yeah, I've got my alkene attacking my bromine. That bond breaks. We've got one bromine on one carbon, a positive charge on the other, and then the bromine with a negative charge comes in to attack to form this as our product. Again, it's always the atom closest to the double bond that gets the delta positive charge. So these are non-polar molecules, but the atom closest to the alkene becomes delta positive. Down below, there is a difference in electronegativity, so it has to be hydrogen, but again, I'll draw the hydrogen closer to the alkene. I'm attacking, break that bond, end up with a positive charge, the chlorine comes back in and attacks, and you end up with the chlorine. So again, you can show the hydrogen if you want to, but you don't have to. Again, this is a symmetrical alkene, so I'm only forming one product. At the end, you've got an unsymmetrical alkene, so I am going to get two different products because I'm adding a hydrogen, I'm adding two different atoms, and I've got two different carbons. So I've got two potential products here. When I draw out the mechanism, again, it starts in the same way. I attack the hydrogen, those electrons move on to the bromine. Sorry. And they move on to the bromine. And I've got two different options. I can either add the hydrogen to this carbon here, which puts a positive charge here, or I can add the hydrogen up on top, which puts the positive charge here. So you can add in those hydrogens if it makes it easier for you to see what you're doing. The bromine will attack to form this product, and the bromine will attack to form this product. And I've labeled this one as major and this one as minor. If we have a look here, we should be able to see why. Here, the carbon with a positive charge is bonded to 1, 2, 3 other carbons. That makes it a tertiary carbocation. Here, the carbon with a positive charge is bonded to 1, 2 other carbons. It makes it a secondary carbocation. The more carbons you've got on your carbocation, the more stable it will be. And your major product forms via your most stable intermediate, because this intermediate is most stable, this intermediate is most likely to form, therefore your major product will be this product here. That's the end of the mechanisms. Then we've just got some reactions to complete. So here you've got an unsymmetrical alkene, you've got two different atoms, so you've got two potential products. Here, hydrogen, you're using nickel, that's your reagent, make sure you know it. Chlorine, you're going to add a chlorine to one carbon and a chlorine to the other, so you're going to end up with this. H2O, it's a gas, it's steam you're reacting with in the presence of an acid catalyst. This is an unsymmetrical, because you've got this methyl group here, not all carbons on the ring are the same, so you do have two different products depending on where you put the OH. Here you're adding H2O gas, again this is oh wait, no, this one I just asked you for the reagents, didn't I? Yeah, so I gave you the product. You could have another product, you could put the OH on the end as well, but I just wanted the reagents. So H2O as a gas. If you just wrote H2O, you don't get the mark. You have to say it's a gas, or you can write the word steam, and you've got your acid. Down here, I'm adding bromine, so one to each carbon. Make sure you don't do what I did and add them to the same carbon. They should be on different carbons. Here, it's not symmetrical, so you have got, again, I gave you the product, didn't I? I was just asking for the reagent, so it's just HCl. If you're adding one chlorine, it's going to be HCl. And then down here at the end, I'm reacting with Cl2, and I'm getting two chlorines. The alkene is not symmetrical, but because I'm adding the same atom to each carbon, it doesn't matter. I'm going to get just the one product. This topic, reactions of alkenes, super important going forward. It comes up again in chapter 16. It comes up again in chapter 25. Really important that you know the products of your alkene reactions and that you can do those curly arrow mechanisms.